All right, let's go ahead and get started here. So tomorrow in the lab, Civil Engineering 319, Lab 2 report is due at 2 p.m. You have to upload it to MU Online before 2 o'clock, regardless of what time your lab is. It's an abbreviated report. As it says on the assignment handout, it doesn't have to be the full report that has all of those same elements on the rubric. So if you want the details on what you need to submit, there's a pretty lengthy section at the end of the report on the back page. It says submit, and it explains that it should be more of a narrative of what you saw and observed, as well as the calculations related to capillary rise and so on. So just review the submit section. It doesn't have to be a full-fledged lab report for this one. Although the lab we're going to do tomorrow, Lab 3, there is a full report associated with that. I've already posted the handout for Lab 3 if you'd like to kind of familiarize yourself with the procedure and in particular the sketch. There is a drawing of what we're going to be working with tomorrow, and the dimensions on that sketch take a little bit of time to figure out. So please go ahead and take an advanced look at that. Also, your next homework assignment is due a week from today, and on problem 66 you need to both provide an explanation and also do the calculations for that one. So it's not just a short answer, but also supporting numbers. All right, so we're going to be talking about hydrostatic forces on flat surfaces today. And that's also the subject of tomorrow's lab, so it's good timing that the two line up like that. Before we start on this new material, are there any questions related to what we went over in class last week? All right. One of the resources that you'll need to have available is the formulas for area moment of inertia. And hopefully that kind of rings a bell as something that you remember from statics and dynamics. In your appendix of the book, it provides the formula for area moments of inertia for different shapes. Here's another resource that sometimes we'll come back to get the area moment of inertia. The thing that we'll be using is the horizontal area moment of inertia. And so since the water line is a horizontal line against shapes, then it'll be the horizontal area moment of inertia that we'll occasionally refer to. And so here are the formulas for a variety of shapes that we'll have to be aware of. Now, the types of questions that we're going to solve, these are applications of the hydrostatic equation. The hydrostatic equation that we've been using so far, we've used it to calculate what's the pressure. But what we want to know in these problems is what's the force. And remember, the relationship between pressure and force is pressure times area. So the hydrostatic equation will tell us at a certain depth what is the pressure that's being experienced. But the thing is that in problems like this, there's a variety of depths that the water is acting against. So consider the case of a gate where the water is pushing on this gate and the force of the water wants to open the gate. So the water is pushing towards the right, and because it's hinged at the top, if we don't apply some sort of a force at the bottom, then that's going to force the gate open and water will spill out. So this is the type of question that we're going to try and solve. How hard is the water pushing on the gate? Or how hard would we have to push on the gate to resist the force of the water? Those are the types of questions that you can expect to see. You'll notice in this drawing we are given some dimensions. We're told what the fluid is, and both of those will be important in trying to answer this type of question. We'll also need to have some sort of a dimension that tells us not just the length of the gate, but also how wide it is. And you'll notice that this dimension here that I'm referring to as B, that's the submerged height of the gate. There's also this parameter that the gate itself is a total of 5 meters in from the top edge to the bottom edge, but it's only the 4 meters that's submerged. And that's because the applicable forces only depend on how much of a certain shape is beneath the waterline. So it doesn't matter what's up here in the air. If we wanted to find out how hard is the water pushing on the gate, it just depends on how much of the gate is beneath the water. So it's the width of it and the height of it. And you'll notice that I've labeled the width A and the height B. And the reason for that is if we go back to these area moment of inertia formulas, for a rectangle, the area moment of inertia, I equals AB cubed divided by 12. So if we go back to the sketch of this gate that we're interested in, when we calculate the area moment of inertia, it's the depth parameter that we would cube. It's going to be, when you calculate the moment of inertia of a submerged shape, it's that vertical distance that's more important than the horizontal distance. So I try and help you remember, which of the parameters to cube by emphasizing that it's the vertical distance that's kind of, in a way, more important in affecting the magnitude of the force. We'll get into all of these bits. Now, what do you suppose this little animation that I've just put on screen here, why does it have that shape? The shape that it does. If you look on the screen, you can see that it's a triangular distribution. And so what does that set of arrows represent? Okay, it represents pressure, and the effect is there's more pressure at the bottom. And the one last thing we can say about it is there's a linear increase in pressure. And remember that gamma is the rate of pressure increase. It tells us how many newtons per meter squared increase with each meter of depth. So the units of gamma are Newton per meter cubed, because it tells us, like if we look at what is gamma, from the hydrostatic equation we said delta P is delta H times gamma. So gamma is delta P divided by delta H. So it is how much the pressure increases per unit of depth that we go downward. So keep in mind that it's a linear distribution. The pressure is increasing. So up at the top edge, where we've got air, there's zero pressure there. So this triangle starts at 0, this triangular pressure distribution, and then it increases linearly as we go down. So what's the formula for force in terms of pressure? Pressure times area. So force is pressure times area. If we want to know how hard is the water pushing on the gate, in other words, if we were going to represent this pressure distribution as just a single one force, like a single force that's applied instead of like that spread out pressure, what this is asking is how big is it? We're also going to be interested in where is it. So where is the equivalent force, and what's the magnitude of the equivalent force? But the tricky thing is, so that formula says force is pressure times area, but which pressure? Because we've got a bunch of different pressures. We've got up here at the top, the pressure is 0. Down at the bottom, the pressure is really big. In the middle, the pressure is kind of in the middle. So that's one of the complicating factors. It's not so bad on a flat surface like this that's vertically oriented. But one of the things that's going to get tricky for us is when we have curved shapes, or when maybe the shape is fully submerged under the water. And so then we have like a variety of different methods to handle that. But I just want to draw your attention to what we're starting with today of these being flat surfaces. These are kind of like unnaturally simple problems because in a case of a triangular distribution, it's relatively easy to identify the location and the magnitude of where that force is. We have to be aware of the centroid. And another thing that was on that series of equations that we had here, it was not just the area's moment of inertia, but also the centroids of different shapes. And so it's pretty easy for a rectangular shape. The centroid is halfway down and halfway side to side. It's like in the center, the centroid. So it's easy, just by inspection. The centroid that we'd be interested in doesn't take into account the full height of that plate. It would just be the submerged portion where water is in contact with the plate. So you'll notice that this dimension B doesn't go down to the bottom edge of the plate as well. It doesn't go to the top, and it doesn't go down to the bottom. And the reason why it doesn't go down to the bottom is it's only referring to that portion of that plate that's receiving pressure from the fluid that's touching it. So when we want to find the centroid, we are looking for the center of area vertically. This one's representing the vertical component of the centroid. It's halfway between the air surface and the bottom where the water is applied. And it's even easier to pin down where the centroid is in this side view because it's just 1/2 of A. So 1/2 of B and 1/2 of A, that tells us where is the centroid, the center of area. And the reason why we care where is the centroid is we want to know what's the pressure at that spot. Because it's the center of pressure that we put into the formula, force is pressure times area. So pressure at the centroid is the key pressure that we have to substitute into that formula to find the magnitude of the force. All right, so let's just review pressure distribution in a little bit more detail, because this problem was unnaturally simple because the gate went all the way to the top and it started at 0 pressure, and so it was just this nice simple triangle. What if the gate doesn't go all the way to the top of the water line? What if it's partially submerged, like shows here? So we can find the centroid. It's just in the middle. B is the entire height of that gate because it's fully submerged. A is the entire width of the gate. So the centroid is at 1/2 B and 1/2 A. The pressure distribution wouldn't start at 0. So what we'd do is we'd extend this triangle up, and the triangle would start at 0 at the top, but since the gate only begins at some depth, then we'd have like a trapezoidal pressure distribution. So it gets a little bit more tricky, but still what we can do is we can find the pressure at the centroid by just measuring how deep beneath the surface is that center of pressure. And we calculate the force once we find the pressure at the centroid. The magnitude of the force will just be the pressure at the centroid multiplied by the area of the shape. Now, in the first example, in this one, because it's a triangular distribution, the force is 2/3 of the way down. Because, I mean, you maybe remember that the centroid of a triangle is 2/3 of the way from the pointy end. So, you know, it's, here's the center of area. It's 2/3 from the top and 1/3 from the bottom to that centroid. So that's this force, the location of the force was 2/3 of the way down because of that, that effect of the force being located at the center of pressure. Now in this case, what this was illustrating is that because it doesn't go to 0 at the edge, the force isn't 2/3 of the way down the plate now. Now the centroid and the location of the force are at different spots. So we have to have like a more sophisticated tool to identify the location of the force than just being able to say, well, it's 2/3 of the way down if it's a triangle, because it's not always a triangle. This is an illustration of the many, many cases where it's some sort of a pressure distribution other than triangular. So what we also need is we need some sort of a formula that tells us where the force is located. So we want to know the magnitude of the force and the force location. All right, before we get into that approach, let's just define some terminology here. First of all, we're going to use delta H to represent the vertical distance from the centroid to the water surface. And delta H is the same delta H that we've been using in the hydrostatic equation. So it's going to be the delta H that we use to find the change in pressure. So here in this little tank of water, I have an inclined plate, and so it's flat, but this time instead of being vertically oriented, it's at an angle. And that changes a few things around a bit. You'll notice here that A is the height parameter that I get from a side view, but then I need like a front-facing view to be able to see the width of the plate, and that's the B parameter if I'm going to calculate the area moment of inertia. So delta H, I used to be able to draw on the screens back in the good old days, but I get in trouble when I do that now, so I'll just gesture with my hands. Delta H is this distance, so you can draw it on your notes. It's from the center, that red dot, straight up. Okay? So delta H starts at the centroid and it just goes up to the water surface. It's the vertical distance from the centroid to the water surface. And that's what tells you the pressure at the centroid. Now, how do we calculate the pressure at the centroid? Well, it's delta H times gamma, same as it's always been for the hydrostatic equation. Now, y bar is the inclined distance from the centroid to the surface. Now, let me show you the difference between the inclined distance and the vertical distance. Here's the water. Here's our angled plate we're looking at as a side view. If this was the centroid, then delta H went straight up to the surface. This was delta H. But y bar is this direction, up to the surface. It's at the same angle. That's y bar. And we need to know y bar because the formula we have that tells us the location of the force requires us to know y bar. So y bar is the distance from the centroid in the direction of the inclined plane up to the water surface. So delta H is straight up, y bar is at an angle, and it stops at the water surface. Yeah?
What if the plate or whatever we were talking about was positioned so that like a dotted line from y bar went to like the edge of the tank?
You mean if the plate was horizontal?
Like,
Oh, okay. Yeah, I get you. What if the water stops here? This is the water, right? Okay. So you extend it out to where the water would be. That's a great question. I'm really glad you asked that. He's thinking ahead. He's thinking, well, what if there's ever a case where I can't measure to the water surface? So you extend the water line out that way. Thank you for that. Anybody else have a good question? I like good questions. All right, so there's the water line. It goes, here is y bar. Now let me show you something. Sometimes the way that we dimension, I may not be able to put that line right on top of where I want it. So what I might do is I might offset that dimension. I might say, this is y bar. So that's the same distance, like I'm still going up to the surface, but like I'm kind of just moving the labels off to the side. So that's still to the water surface, but just moving like the dimension labels off to the side a bit. Y bar. YCP, the inclined distance from the water surface to the center of pressure. Now, the location of the force is always going to be below the centroid, always. If we go back to this other drawing here, the location that the force is applied is always below the centroid because there's more pressure on the lower half of the plate than there is on the top half of the plate. So that brings the average down below the middle point. Does everybody get that thing that, you know, if you just look at how much green is there above the centroid versus below it, you know, the magnitude of that green, it's like we're integrating the pressure over area, and that tells us the force. Well, we're also integrating the location of that force, and more of that force is going to be below the centroid than above it. So the location of the force is always going to be a little bit lower than the centroid, and what we call where that force is applied, we call that the center of pressure. There's the center of area, which is the centroid, and the center of pressure is where the force is applied. So it's always below the centroid. And the center of pressure is the inclined distance from the water surface to where the force is located. So now on this sketch, see this green arrow that I've just put on? That green arrow is where the equivalent force, put your phone away please. This green arrow is where the force is applied, and so what we're going to have to do is have a dimension that takes the distance, the inclined distance, up to the water surface from the green arrow. And so the center of pressure where the force is located, this red dot is the distance from the surface to the centroid. So here I'm going to draw the equivalent force. And now that dimension here is YCP. So remember, Y bar was just to the centroid, but YCP is to where the force is applied. Yes?
Does the force always act perpendicular to the bottom?
Yes. Yeah, so he's asking about the direction of the force. And it does act perpendicular to the flat plane. When it's a curved surface that the force is acting on, we'll break it up into vertical and horizontal forces. But when it's flat, we'll just say there's one single equivalent force which is acting perpendicular to the orientation of the plate. Other questions? Okay, so here's the formula that allows us to calculate YCP. And YCP, again, that's important because that's where the force is located. That's the dimension that allows you to identify the resultant force. If we're going to say we're integrating that range of pressures, there's a whole lot of pressures acting over a lot of little different areas. If we wanted to break it up into tiny little squares like a mesh, well, the equivalent single force applied at a single location is located at YCP. And so we have to know the Y bar formula, location, which is to the centroid, and then we use the area moment of inertia, I, and then the Y bar times A. So it tells us that YCP is going to be at least Y bar and then some additional distance below the centroid. And so going back to this formula, another way that we'll sometimes use this formula is sometimes we'll ask how far apart is the center of pressure and the center of area. So we could rearrange that formula to be YCP minus Y bar is equal to I divided by Y bar A. And what that allows us to do is say, if I zoom in on this plate a little bit, all right, here's the center of area, here's where the force is applied. That distance is this, the gap between the centroid, the center of area, and the center of pressure. So once in a while you'll see me rearrange this formula because we don't necessarily want to measure where the force is up to the water surface. Sometimes we're just caring how far apart it is from the centroid to where the force is applied. So that'll be a trick that we use on one of the examples. Does everybody understand the variables that are in this formula? Which formula we use for I varies on the shape of the plate. If it's circular or elliptical or rectangular, sometimes we'll have different formulas for I. All right, so let's go back to this type of problem. How do we find out what's the magnitude and the location of the hydrostatic force? And then also, how much of a force would we need to apply to resist that? In the case of water at 20 degrees Celsius and a 4-meter tall, 3-meter wide plate. All right, so for this one, first of all, we want to find out the distance to the centroid. So step 1, we want to know delta H. Okay, so the centroid is halfway down the submerged depth of the plate. So we can see that the dimension of 4 meters from the hinge to the bottom edge where the plate is in contact is 4 meters. So delta H is 2 meters. That's the vertical distance from the water surface to the centroid. Okay, step 2, we want to know the pressure at the centroid. Pressure at centroid. Okay, the formula we use for calculating pressures is just the hydrostatic equation. So it's going to be delta P is delta H times gamma. The pressure at the centroid, sometimes we call that P bar. So I'm going to say P bar is delta H times gamma. We can substitute in the information that we've got there. So it's 2 meters of depth, and for 20 degrees Celsius water, it's 9790 newtons per meter cubed. So the pressure at the centroid is 19,580 newtons per meter squared. So that's what the pressure is at the centroid of the plate. Now step 3, what we want to find is the hydrostatic force magnitude. So let me just transfer this little sketch here. We've got 4 meters by 3 meters. And the water is up to the edge. All right. So step 3, find the hydrostatic force. And the force that we're talking about is the water pushing on the gate. So from the side view, we have this gate is 4 meters tall. All right, so we want to know, here's the centroid. It's at 2 meters, and the force is acting below it. So what force is the water pushing on that gate? So it's F is going to be the P bar, so the pressure at the centroid times the area. So the pressure at the centroid we previously determined was 19,580 newtons per meter squared. And multiply it by the area of the plate, and that's a 3 by 4 meter plate, so that's 12 square meters. And so if we multiply that area by the pressure, the magnitude of the hydrostatic force is 234,960 newtons. All right, step 4, let's find the location of the force. Location. Since it's vertically oriented, y bar is the same thing as delta H, because here's the centroid, and if we go from the centroid up to the surface, that's 2 meters, and the inclined distance from the centroid to the surface is also 2 meters. Since it's not at an angle, delta H and y bar are the same because it's vertically oriented. So we need to calculate the area moment of inertia. So I equals AB cubed divided by 12. And the A parameter is 3 meters. The B parameter is 4 meters cubed divided by 12. It's 16 meters to the 4th. Okay, and the reason why we wanted to calculate the area moment of inertia is, remember, our formula for YCP is going to be y bar plus I divided by y bar A. Okay, and so we know y bar is 2 meters, and area moment of inertia is 16 meters to the fourth. Y is 2 meters, and we're multiplying that by our area of 12 square meters. So that's 2.667 meters. So that's the distance from the surface down to where the force is located. So when the screen warms up here, I'll show you what it's talking about. So 2.667 meters from the water surface down to where the force is applied. And remember, what we said before was, since it's a triangular distribution, this is an easy problem. It's just 2/3 of the way down. And this 2.667, that's the same thing as 2/3 of 4 meters. So it works out based on what we were expecting. It checks out so far. The last thing it's asking for is the magnitude of this force that we would have to apply to keep the gate closed. Like, because you've got the water giving a counterclockwise rotation due to the hinge, and so we have to apply some force to keep that gate so that it doesn't open. So if we know that there is this hydrostatic force with a magnitude of 234,960 newtons, and it's located 2.667 meters from the hinge, and we're going to resist that with a clockwise moment, magnitude F unknown, and the distance is 4 meters, then we can just do that moment analysis and find out that the force we'd have to apply would be 156,640 newtons to resist it. Okay, so that's among the simpler hydrostatic force type problems that you'll see, but the same process we can apply and adapt for other more complicated problems. We can always find out what is delta H, calculate the magnitude of the pressure at the centroid, and calculate the hydrostatic force based on the pressure at the centroid and the area. Then we'll have to try and find the location of the force, and it's not always going to be the case that delta H and y bar are the same. Who can rephrase why is it that in this case delta H and y bar is the same? That's exactly right. It's because the plate is not at an angle. It's vertically oriented. If it was at an angle, we'd have some geometry on our hands. You're going to remember, you're going to be doing like, okay, 3, 4, 5 triangles, cosine this, sine that. You have to dust that off. Maybe it's been a while since you used much geometry. You'll use some this semester. Any questions about this example? All right, so here's what I'm going to do. I'm going to stop talking and allow you to collaborate with your classmates. We got a similar problem here. We have a gate that is 2 meters wide, 3 meters tall. It's fully submerged, so the edge of the gate doesn't go up to the water surface. But it is vertically oriented, so at least delta H and y bar will be the same for this problem. What I'd like you to do is find out the magnitude and the location of the hydrostatic force that's acting on the gate. So we're not doing that like resisting the gate. That moment balance part doesn't apply for this problem. But do calculate the magnitude and the location of the hydrostatic force. So since we're specified the water temperature is 20 Celsius, we have to use a unit weight that's specifically for that temperature. So we're going to use 9790 again for gamma. And so we've talked about why delta H is 4.5 meters, because we've got the ½ meter from the centroid of the plate to the hinge, and then 3 meters from the hinge up to the water surface. So that means it's a total of 4.5 meters deep to the centroid. And to find the pressure at the centroid, we just combine the depth to the centroid, which is 4.5, and the 9790 newtons per meter cubed. And so that tells us the change in pressure from the surface down to where that center of area is. The centroid is 44,000 pascals. And then to find the magnitude of the force, we apply the pressure at the centroid times area formula. So the magnitude of the force, 264,330 newtons. All right, and then to find the location, we do the area moment of inertia for this particular shape. Since it's a 2 by 3, 2 is the vertical, 2 is the width, 3 is the vertical, so we're cubing the vertical parameter. So that gives us the area moment of inertia of 4.5 meters to the fourth. And then we want to find YCP. Since it's vertically oriented, then that's going to tell us the vertical distance from the force location to the surface. So the location should be 4.667 meters down. Okay, so there's the entire solution. Anything that doesn't make sense in this procedure or how we applied it to this problem? So the trick was how the, if there was a trick, the trick was how it was dimensioned. It's not always going to be a case where they point out, here is the centroid, and here is the delta H parameter. Sometimes you'll have to do some subtraction, and for the lab, that's why I wanted you to kind of get an advanced look at the dimensions that's on the drawing I provide for tomorrow's lab handout. It's kind of the dimensioning that's the crux of the whole experiment. Everything else is pretty straightforward, but once you figure out the distances from the water line to where the force is applied, then it'll be easy. But you can't at first glance immediately make sense of the dimensions. It's something that you have to kind of reason through a little bit.
Regarding the B value on this example, I know the last one, it was mentioned from the water line down to the bottom of the gate, but since this gate is already submerged, since we're only talking about the force on the gate, then you wouldn't necessarily measure from the water line
Right.
down to the bottom of the gate because you have that kind of empty space.
Right, good point. Yeah, so in this case, it's the physical height of the gate, not the submerged height of the gate, because all of it is submerged. So we're talking about the force just on this section of metal that's beneath the hinge and above the concrete. So, there is also forces acting on other things. Like there is a hydrostatic force acting on this wall, and there are forces that are acting downward on the bottom of whatever this is. But since it's just this certain gate, the 3 meters by 2 meter gate that we're interested in, then we use the full height because it's all submerged. Yeah, I'm glad you asked about that. Are there other questions? All right, so here's a tricky one because it's in, go ahead.
So when you calculate the area that you use,
Yes.
I think it was the third section. So that's when you only use 50 by 3 and you don't include that top section.
The area of the plate, it's the area that's in contact with water. So in this in this second example, the entire plate was in contact with water, but in this first one, the area that we used was just the submerged. So we neglected this top part of the plate because it was in contact with air in the first example.
The plate or the part that's above that plate was the delta H at the
No, I think on this we said the delta H was from the water surface down to the centroid. So I think this 1 meter above it, that's irrelevant information.
Yeah, but on the other, when I was
Okay. So on this one,
Like the only time that you use the top section above the shaft.
yes, that's right. Right, okay. Yeah, so that extra 3 meters from the hinge to the water surface we just used for the delta H. Yeah, great. Okay, so let's complicate things a little bit by inclining the plate. And the reason why this complicates things is now delta H is the vertical distance from the centroid to the water surface. Y bar is the inclined distance from the centroid to the water surface. And then YCP is the distance from where the force is located up to the surface. So those 3 parameters are all going to be different in this example. All right, so we've got a 2 meter wide plate. From the front view, we can only see how wide the plate is. We can't dimension how tall the plate is from the front view because it's at an angle. So we rely on that side view to show us that the plate is 3 meters tall. You can see that the angle is a 45-degree angle up to the water surface. Now we can follow the same 4-step procedure. Depth of the centroid, magnitude of the force is dependent on the pressure of the centroid multiplied by the area. Area moment of inertia, and the location of the force. I guess that's a different 4 steps, but ultimately they're numbered differently, but it's the same stuff as before. It's rectangular. The dimensions are given. So I'm again going to pause this one and give you some time to think about the geometry of finding out those parameters. So let me erase these sketches that we had before and just aid you with one little hint. So that is, here's the water surface, here's the plate at an angle, here's the centroid halfway down the plate. So again, what our dimensions are is delta H is straight up to the water surface, Y bar is the inclined distance, and then YCP is that parameter from where the force is located up to the water surface. All right.
My thought is that it's a long way. So the sine for my thought is delta H or Y bar. What you said, Y bar. Oh no, you're right. You're right.
All right, I've got the solution up here on the screen if you want to check what you're doing versus what I calculated. So to find the depth of the centroid, it's the 5 meters to the edge. So from the water surface to the edge is given as 5. And then we want to know the vertical component of that 1.5 meters. That's the distance from the edge of the plate to the centroid. So the vertical component of that is just going to be 0.7071 times 1.5. So the overall delta H is 6.061 meters. And then that's the depth you use to calculate the magnitude of the force. Remember, the magnitude of the force is the pressure at the centroid multiplied by the area. In this problem, I didn't tell you the water was at 20 Celsius, and so it's a minor point, but the gamma I used is 9810, the kind of default value for the unit weight of water. So we've got the 6 meter squared area, the unit weight of the water, the depth of the centroid, and it all works out to about 356 kilonewtons. And then we want to know where is the force located. So it's going to be using the area moment of inertia formula to find I. And then here you can see I'm stumbling through the geometry of finding the Y bar, the inclined distance from the centroid to the water surface. And so we had the delta H depth of 6.061 meters. And so now we can find the inclined version of that distance. Rather than going straight to the surface, we're following along the same angle that the plate is rotated. So That's 8.572 meters. And then in the end, when we combine that with the ratio of the area moment of inertia times y bar A, then the location of the force is always just a little bit lower down on the plate than the center of the area, the centroid. So you can see there's not that much difference between the location of the force and the centroid. And the deeper you get, the closer those two get together. As you continue to submerge a plate lower and lower and lower, the distance between them, the gap distance, decreases. All right, so that was an inclined plate where the y bar and the YCP had to be calculated because it's not straight up and down. Any questions or curiosities about this example? All right, well, let's continue this with just get more practice. I know that the examples are helpful to make you feel prepared for the homework. So we're going to work through as many of these examples as we can today. If we have a pipe going into a tank and put a gate on the front face of that pipe, if we cut the pipe at an angle, then what we end up with is an elliptical gate shape. And the way that you can kind of think of that is, take a piece of paper and roll it into a tube. So we're thinking in 3 dimensions here. We've got a pipe that goes into the tank, and we want it to be, the gate is at an angle. So think about if you cut that cylinder at an angle, then the front face of it isn't going to be circular anymore. It's circular only when this is flat. But when you cut it at an angle, now that opening is an elliptical shape. So if you wanted to cover it so that water doesn't leak through the pipe, then the shape of the gate has to be elliptical. And so in this case, if we have a 4-meter diameter pipe and the length from top to bottom is 5 meters, then the shape that we're looking at in the area moment of inertia formulas, the way that they dimension an ellipse is A is the distance from the centroid to the edge. This is A. And B is the distance from the centroid to the top edge, the vertical. So whereas in the rectangular it was like the full distance, for an ellipse it's just half the distance. Okay? I wanted to point that out because here we have, I guess it's already on the screen. So we've got the elliptical shape, we know what A is, we know what B is, so here's the formula for both the area moment of inertia and the formula for the area of it. Okay, so it's kind of the same basic process as we've been through before. We want to find out, in order to know the magnitude of the force that's acting on this gate, we have to know what is the depth to the centroid, the pressure at the centroid, and then to find the location of the force, we have to look at the inclined distance to the center of pressure. Let me refresh my memory on how many more examples we've got besides this one, because we've only got, this is the last one. All right, that works out. We will have enough time. So see if you can figure out the magnitude of the hydrostatic force. Even if you don't have enough time to do all of the location of the force stuff, I think you will have enough time before I show the solution up on the screen to identify what's the magnitude of the force. And remember, the magnitude of the force depends on the pressure at the centroid multiplied by the area. So the question is, where's the centroid on that gate? So where is the centroid? Okay. The center of that ellipse is 2.5 meters down the edge, because if it's 5 meters from top to bottom, 2.5 is half of that. But what is the vertical distance from the hinge to the centroid? It's actually really easy. They tell us it's a 4-meter diameter pipe. So halfway down that 4-meter diameter, so the vertical component of that is 2 meters. So the delta H for this, delta H is the 8 meters to the edge plus 2 meters, which is the vertical component of the distance from the hinge to the centroid. So the physical distance is 2.5, but the vertical distance is just 2. So delta H is 10 meters. And so we can find the magnitude of the force. The force is the pressure at the centroid times the area. So that is delta H times gamma times the area. Okay, so that's 10 meters times the unit weight. And this is just water that's in there. So 9810 newtons per meter cubed. And then the area of this ellipse, area is pi a. So a is the width parameter. So that is 2 meters. And then the b parameter is that half of the height. So that's 2.5 meters. So the area is 15.708 meters squared. So multiply that by 15.708 meters squared. So the magnitude of the force should be 1.541 meganewtons. That's 1.541 times 10 to the 6th newtons. Since we've only got a handful of minutes left, let me bring up the solution on the screen so you can follow through how I calculated the location of the force. And of course, you're welcome to copy that into your notes. Let's talk through it here. Okay, so that's the wrong one, right? Where is it? Yeah, there we go. All right. So the depth of the centroid, the force at the centroid. Now, where is that force located? So think about similar triangles. And so we know that the gate is at a 3-4-5 angle. It's 4 meters is the vertical component of the gate, and 5 meters is the physical length of it. So that same angle defines the distance delta y, because what we're saying is the 10 meters was delta h, and the definition of y bar is the inclined distance from the centroid to the water surface. And so if 10 meters is the vertical distance and y bar is the inclined distance, we're saying that 10 is to 4 in that triangle, as 5 is to delta y in that triangle. And so through similar triangles, I calculated the y bar, here setting 10 is equivalent to y bar, 4 is equivalent to 5, the ratios there. So then you solve for the y bar distance. That's 12.5 meters is the inclined distance to the centroid. And so then to calculate the actual physical location of it, here I did the difference, the ycp minus y bar. So that's a way of calculating how far from the centroid to the location of the force. And so let me go back down here to the drawing I have at the very end. So the distance between the centroid and where the force is applied is 0.125 meters. And so this gap right here is 0.125 meters. So that means from the hinge to where the force is located is the 2.5, which is half, plus then that little difference that's defined by the YCP minus Y bar. So 0.125 meters is added on to the 2.5. So that's where the 1.54 meganewtons is applied. And then if we wanted to know how much does this force have to be pulled in order to open up the gate to resist all that hydrostatic force, well then it's going to be the full distance of 5 meters that the force is applied. So you've got the 1.541 meganewtons that's acting counterclockwise at this distance away from the hinge, and then it's resisted by the opening force F. So you'd have to open with 0.809 meganewtons. So hopefully that's giving you a taste of the geometry. That's all we've got time for today. So remember that the next homework assignment that you've got due, you could get an early start on that, and I'd encourage you to. It's not due until September the 18th, but definitely you can start tackling some of those questions, and let me know if you've got any questions.